Good evening. Honored to be concluding today's talks with one more in a series of talks on mobile security weaknesses, in particular cryptographic weaknesses. Quick recap on what happened so far. GSM was broken and broken and broken again on different levels, and it's now acknowledged that calls and text messages are easy to intercept. They're easy to intercept mostly because the encryption function doesn't hold up to what you would expect in the internet age. It's a 64-bit encryption function that allowed us to compute rainbow tables to break them. And we were finally done, and everything was acknowledged as broken. We thought we finally ran out of widely used weak encryption function. Who today would use a proprietary encryption function in a system with billions of users? GSM, of course, is decades old. Dates back to Cold War days where people did try to keep their cryptography secret and weak enough so the Russians wouldn't get an edge. We did find one more though, so the sadness for cryptographers is over. Today, they will get one more toy cipher, a proprietary stream cipher used to, again, secure a system with billions of devices, one that provides the information backbone for mobile societies, gprs, what all of our phones use to connect to the internet when they don't happen to be 3G. So GPRS is very much an important network by itself, but also a scale-back network for where 3G is not available. Besides mobile phones, though, a lot of other lower throughput devices that need to exchange data do connect predominantly over GPRS. Industry automation, robots receiving their new firmwares and interesting things like that. Most toll gates will talk over GPRS and communicate people's driving behavior, and a lot of new rollouts. Most power meters we have seen being rolled out in Germany use GPRS to communicate electricity usage back to some central system. Most of these communication links trust in the security that GPS provides, the security that the big telecom operators did build into the GPRS networks. Now, we're here today to challenge that belief and to inform about the weaknesses found in this network used by billions of devices. So in theory, GPRS does a few things better than GSM. It does, for instance, encrypt data more end-to-end, not from device to device where you would imagine end-to-end, but from the two ends of the radio link as the mobile operator sees it, from the device itself all the way back to a central system, usually one per country, where then data is decrypted. So this already allows for much less intercept than in the GSM network, where every microwave connection between a base station and a cluster server for several base stations would be unencrypted. So people did give this some more thought than was GSM. However, it did also come 10 years later. So if anything, we wouldn't expect weak cryptography to be in here, of course. The Cold War was long over, and people actually understood how to build cryptography a lot better. There was a lot of progress made, especially around stream ciphers in those 10 years between the big GSM launches and GPRS's launch. But let's investigate that a little further. GPRS does offer a whole number of different security levels in form of different encryption functions. There is the option of using no encryption at all. GSM also offers this, and some repressive countries actually don't want any encryption used by anybody, so it's in use. GPRS offers the same option. So you'd think that the same countries may also not allow GPRS usage. We don't go to most of these countries, so we can't confirm or deny that about those countries, but we'll get back to this point a little later on. Then there's two encryption functions that were built into GPRS from day one, the GA1 and 2 stream ciphers. They have so far been completely secret, as the A51 cipher was completely secret when GSM first launched, but a couple years in, I think Ross Anderson got an envelope in the mail with a description of the cipher, and he posted it on, I think, the crypto mailing list. No such envelope has yet been sent for GPRS, so this encryption cipher is still secret. Shouldn't be, though. You may have noticed a stunning lack of security research into GPRS. Much is being said about the data about the voice communication on mobile networks, but very little is actually investigated on whether the data is being exchanged. And personally, I believe that's because these encryption functions have never been published. They may soon be, though. There are better options than these all proprietary ciphers. So even though the ciphers were never declared weak, today the understanding is that you shouldn't be using secret ciphers to begin with. And so the encryption ciphers of UMTS 3G have been backported into GPRS around 2003, I believe. However, even today, there's very little adoption of this backport. Even though, of course, the phones today implement this cipher, clearly the phone has to have it anyway to speak UMTS, so why not also use it for GPRS? In fact, why not also use it for GSM? There's a long-standing proposal to adapt the cipher called A53, which again is the very same cipher, the Kasumi cipher. So this one acknowledged good cipher could be used for anything the phone does, in fact simplifying matters. But this is very little found. And then yet a more recent proposal to not only use the same cipher, but also the same key lengths and internet age grade key lengths of 128-bit. That proposal, of course, isn't even debated in these communities. So they're at least 2 steps behind now from what we would call normal security. We looked into this for about a year now, not wanting to go step by step as with GSM, where first the GSM told us, and they were right, that all our attacks were just theoretical, they had to be implemented. We did implement them, to which the GSMA said, well, now they can decrypt data, but they have no way of getting the data into the computer. To which we said, we'll work on that, and we did really several different ways of getting the GSM data into the computer. And today the full system stands. So with GPRS, we wanted to save everybody this long road of discussion, and we went all the steps at once. We won't have time to cover everything today. In particular, we'll leave out the attacks that already worked against GSM. In particular, a fake base station attack, basically an IMSI catcher attack, where you pretend to be your local network operator, and phones will connect to you, and phones will happily, as long as you provide IP access to them, send any data they want to send to the internet through your base station. We find that a lot of that, of course, is unencrypted, since the GPRS network is so far trusted as a secure network. On top, people seem to believe that phones can't execute the expensive cryptography behind SSL very well. So a lot of mobile websites are unencrypted, where the PC version would use SSL encryption. So a simple IMSI catcher attack surprisingly works against all these industry automation systems, all these smart power meters, and of course your phone or PC when it's connected through a mobile network. We're not going to get into that very much today, since the same rules apply as with GSM. Also, we won't discuss rainbow tables. They apply much less to gprs. We'll see why in a slide or two. Suffice it to say, though, that the protection they put in, initialization vector that makes the cryptographic function different in every packet through a random number, that this protection feature isn't used by all operators, at least not in Germany. So until that bug is fixed, rainbow tables actually would work against at least one network here and against all of these ciphers. They're not at GA3 yet, but if they were to go there without fixing these other bugs, this very much applies. Instead of talking about those any further, though, we want to show two things. First, how to get data, GPRS data, into the computer, encrypted or not, and then how to break the GA encryption function. And I'll have Luca explain how the Osmocom phones were modified to deal with GPRS data, and I'll jump back in after his demos to explain the cryptographic parts. Luca, go for it.
Okay. So, good evening. As you may know from other talks, we are using Osmocom hardware and software. And on the left, you can see this mobile. And we started from a branch of Osmocom software, a branch from Sylvain that is somewhere here. This branch allows to capture the raw bars, and since GSM and GPRS are using the same channel encoding, we take the raw bits and then we process in different way, of course. And so we start from the raw bits. To acquire the full stream, we need some little modifications to the Osmocom BB. Like this cable is capable to higher rates, like 4 times the serial normal rates. And this allows to capture 4 time slots with one phone. And of course, it's not enough. And to capture all the time slots, you need 2 mobiles for downlink, 2 mobiles for uplink. So with just 4 mobiles, you get all the data in a cell.
Let me add one thing here, just as a kind of clarification we should have said in the very beginning. So GSM and GPRS, at least the earlier versions of GPRS, don't differ at all in the way they transmit data. The way GPRS achieves higher rate than your old GSM data modem is by using several GSM channels at once. Of course, then intercepting, sniffing it, also requires you to intercept more than 1 GSM call at once. So several of those available time slots that would typically be split across calls are now used in one data connection. And then the edge standard makes each of these channels faster. So that actually is like going from an older modem, like a 14,000 modem, to a 56K modem, right? But still the same security applies. So all of this is just GSM data, sometimes multiplexed on more channels, sometimes using a more efficient modulation algorithm.
Yeah, so from all these parallel channels, we have the tool in the middle that is going to process all the data together. So the first step is multiplex data from multiple phones. Then the harder task is decoding channel and parsing the first protocol on top of the raw bits. That is RLC. And it's quite nice to see. And after this block in the middle, we have the LLC blocks. The LLC blocks are streamed over GSM tab. That is a protocol for GSM that we already used in other applications. And then Wireshark is our friend. And from LLC, you can see the IP packets. So in not encrypted networks, you can actually see IP. And I also developed a RLC dissector that is not fully completed, just for debug, but is actually interesting for future developments.
But you see where we're getting here from a 10-euro phone through open source software into Wireshark. So you may understand the title of the presentation better now, the war driving reference in particular.
Next slide. Just to see some details about what's inside the GPRS decode. So we have at the left all the traffic channels from time slot 0 to time slot 7 for uplink and downlink. For each of them, there is a FIFO, a queue, that shifts the frames until 4 sequential frames are found okay. Then there is some selector that decide what are the modes used. The mode is like, as Carsten was saying, we can encapsulate different amount of data in 4 bars. So it can be from 23 bytes to 53 bytes. And those small packets contains RLC header that is parsed again, and then encode in TBF. TBF is temporary block flow, is the way the BTS allocates some resource to the mobile. So if the mobile wants to transmit, it asks some TBF, and the BTS allocates 1. So each TBF can contain 1 or more IP packets, other communication, and that's it. And this is a hard part, because during defrag, you can miss some packets, so you have to wait and to process and like the window. Okay, I mean, it is quite working, but not really, how to say, properly. Then you can see in the demo before, after, we are going to push the LLC messages outside this tool to Wireshark. So you can actually see IP. Oh, this was just to show
turtles on turtles on turtles.
Yeah, just to show you what happens in GPRS. So there are so many layers. Like from the row bits, there are 3 layers of encapsulation that are not needed. Okay, they are needed, but actually they do the same thing, like defragmentation, user multiplexing, connection multiplexing, and at the end we have these nice data blocks, BSN3 for example, that can contain smaller subblocks like LLC0, a part of LLC1 that is continued in the next, and this makes it so hard, but we actually get it working. So yeah, it's a kind of not really well-engineered protocol, but okay, I don't want to say it. And yeah, the thing I developed is not completely respecting the standard, because it's of course a passive sniffing tool, but okay, it works. So, and yeah, I would like to show you how it works later.
Well, let's do that right now, right?
Oh.
This would be a good time to...
Oh, wait. Do we show the live demo?
Yeah, let's start with some live GPRS capturing. I'd like that. Yeah.
Okay. So I just start mobile.
Do you actually want to sit here? So you can. Oh
no. So I have BTS here. This is private network that I'm using, and I have a SIM card for that. So I have one mobile connected, still not connected. Yeah, connected. Okay.
So this is running the OpenBSC with Osmo SGSN to create a GPRS network.
Yeah.
Of course, a non-encrypting one for now, for demo purposes, and for legal purposes too, a private network where we will only intercept our own data.
Okay, so I start in the sniffer. Okay, you can see some faster messages that are the beacon channel. When I turn on the connection on the mobile, you can see some interleaved white message. Those are the RLSC messages. Now the mobile is just connected, but it's not transmitting anything.
Do we just kill the VNC? Too much data?
Yeah, I just killed this. Maybe it works, okay. Yeah. So I can show you this first thing. I'm going to run GPRS decode on the data I capture right now. Can I use mine? No? Okay. So here there is Wireshark. This is the run. And okay. Those are the first packets the mobile is going to send. Attach some PDP requests, and here you can see the IP of my mobile here on the blue line. Then again, I'm going to use some browser here, and I don't tell you which website I'm going to browse. And then you can see some more white lines. Oh, it's okay, not properly shown, but the red ones are just the raw bits, and the white ones are actually the decoded bars into LLC. Okay, I can just stop. Okay. So I just clear here. Okay. I'm going to decode next capture. And you can see the IP packets here. Some nice query to facebook.com. And the HTTP GET and everything. Like it was like normal sniff.
Like it was an unencrypted Wi-Fi.
Yeah, and then I think we are going something later.
No, let's actually look at some encrypted data. So that can be captured too, of course, with the same setup.
Oh, maybe.
Actually, let's skip that. Let's go right to the meat. Let's show the data you collected in your home country.
Yeah, I was really surprised. What happened is, okay, I get back to Italy, and I, of course, was developing still my decoder, and I have this file. It's decoded.
So this is from a commercial GPRS network in a European country. No suppressive regime. Well,
you can
I'm not saying anything more.
Yeah, the first row, it says protected. That means there is a checksum, but not ciphered information. So next is DNS query to my POP, my mail server, and then again some connection. And okay, I think I cannot show you more here. But I was really surprised that it was all clear.
So we find that there are GPRS networks in Europe, big ones, with no encryption at all. So what's the last time you saw an unencrypted Wi-Fi? A long time ago, huh? They all encrypt now. So here's a whole new abuse potential. So yeah, that's the tool. You saw working here now. Don't let you stop here though. This tool will be released once we get some sleep.
Possible.
Yeah, tomorrow. Once somebody explains to us how to set up a Git repository, we will share this with each of you. We will also run an unencrypted GPRS network for you to test the tool and then take it home and pen test your home GPRS network. There's unencrypted networks in at least 2 countries bordering Germany. There may be many, many more. All right. Oh yeah, that's his SIP number.
Yeah.
If anybody wants to call him, that went unencrypted over the air in that other country.
That was really surprising me. I just connected my mobile to the network, and in the first packets I saw some strange strings like SIP, sipgate.de. Oh, it's my account. And then other things, but okay.
All right, so maybe a third, maybe a quarter of the GPRS networks out there are already broken as of tomorrow's release of this software, and we see no reason for responsible disclosure there, of course. There is a network with no encryption at all that's easily abused with any type of GPRS debug equipment that you could have bought some 10 years ago. So it's a binary switch. Turn on the encryption in those countries and make it better. All these networks that we have seen do encryption for their calls. They don't for data. So there's already key management in place and all. What I'm being told by operators is that the reason they're not switching this on is so they can better monitor the data traffic. They can look into your connection, see whether you're using Skype, cut you off if so, maybe do some malware scanning, but still, things that you wouldn't want to trade in for information privacy over the air. These waves traverse some 30 kilometers, so all your data is being broadcasted over large areas, unencrypted. What if they are encrypted though? Are they safe then? And of course, if the answer was yes, I wouldn't be here. No. So this secret encryption function, we reverse engineered it, of course, as we did with all the other weak encryption functions. And it turns out that every single one, it seems to be a basic rule of making your own proprietary encryption function, does a lot of things right, but at the same time breaks something in the process. So you may remember DECT, where they extended a 64-bit cipher and an 80-bit cipher, did more state, more non-linearity, more of everything, went in the right direction, but then forgot to do enough initialization, and Eric Teves, Ralph Philipp Weimann broke it algebraically. This case, similar. The known attack, even when GPRS came out, against A51 in GSM were rainbow tables. There were some algebraic problems, but they are, to this date, purely academic. So nobody breaks academically. They do it kind of practically, generically, without much thought to it. So it appears that they try to prevent, when building the GA1 function, this one attack only, disregarding all the other attacks the academics had warned about and had been ignored because they couldn't show its practicality. So they much increased the state size. The state size, not the key size, the state size is what makes a cipher resistant against time memory trade-off, rainbow tables. With the little exception, if you don't use an IV, then of course the key size is what matters. So time memory trade-offs in this case should be mostly mitigated. 96 bits is the minimum state. There's a better function with some more state. We haven't looked at it in much detail yet, but it has a very similar algebraic structure. So everything I'm saying now about GA1 should, at some scaling level, also apply to GA2. And GA1 is highly vulnerable against algebraic attacks. Algebraic attacks being those academic attacks that try to solve ciphers smartly, not with brute force, but through equation solving. And there's one key feature, non-linear updating of the cipher state that A51 has, and that the people building A51 took out of the A52, which, if you know the history, you know that this was the export version, the weakened one. So somebody already knew this is a good feature to have, and if you take it out, you can give it to Russia or whichever place. In GA1, they also took it out. Right? So some food for thought here. They did take out the one feature that they knew distinguished a weakened from a full-strength cipher when constructing the GPRS network. Right? It does do nonlinear updating throughout initialization, but this being a stream cipher, the initialization can pretty much be skipped, and when attacking, you can just look at the state after initialization. The second thing that may not have been given a lot of thought is the availability of key stream. So there are A51 attacks that attack the cipher itself and say, if this one cipher generated such and such amount of key stream, then we can break it. Of course, in GSM, it only ever generates 114 bits, 114 bits, 114 bits. It'll never generate any more than that. GPRS completely different. Since it encrypts on a higher level, the encryption spans several GSM frames, in fact, many GSM frames. And it encrypts 1.5 kilobytes total. So those two things taken together, nonlinear update and lots of availability of key streams, now enable people like Mate Sos, somewhere in the audience, to break this encryption function. In fact, since this will take a couple of minutes, let me start one thing in the background while before I'm going any further down the explanation here. So I pre-generated some output bits of the GA cipher, and let's just keep this in the background for now, right? I'll explain what this does. So this algebraic attack works on the fact that the cipher structure is not completely random. I was touching on this topic in my dissertation, and I never really followed up on it until now. A cipher can be, different ciphers can be distinguished in strength by measuring how random the mapping appears from the input bits to the output bits. So imagine a cipher is a system of equations, very simple equations, say ors of ands. So little ant, tuples, triples, quadruples, and all of these all together. So each output bit would be defined as a very long string of odd ends in terms of input bits. Can you see that? So it's some clumsy way of describing any mathematical mapping. And if this has 96 state bits, then there should be quadrillions of possible monomials, they call them, these AND clauses in the description. So it starts with x1, x2, x3, and so forth, and then you have x1 and x2, and then you have x1 and x3, x1 and x4, and then all the way at the end you have x1 and x2, x3, x4, and so forth, right? So can you see this long string? And if the cipher was perfect in some mathematical sense, the distribution of which of these clauses is there and is not there is completely random. There's no structure to it whatsoever. Now this is this exact mapping for the GA cipher. And if this was really random, this should be basically one color, a little noise, but one color. And this, as I'm sure even the people in the very back can see, is not that. It's very structured in many ways. And in fact, it's not just very structured looking at it from this very high level. In fact, to point out a few things, these purple stripes, they start the monomials for each of the LFSRs. So in the beginning of the LFSR, there seems to be more going on than towards the end. So somehow the randomness doesn't distribute throughout the equations very much. And remembering that this doesn't have nonlinear update, how could it, right? Sorry if I lost a couple of people here. Oops. Now, this cipher has some. So this picture has almost some Mandelbrot properties to it, because it's not just structured on this very high level, but it's kind of structured at each zoom level, right? So there are new structures appearing at each of the zoom levels, different structures, and even if you zoom all the way in, there'll still be structures, right? These may be harder to see, but you see this part being more noisy, and then it's kind of doing a little wave here, and then there's a step function here. That's the LFSR update, where things just ripple through the LFSR and don't really get mixed. So I thought this was a neat visualization to show why an encryption function isn't all that strong, and it's obvious from generating a picture of it that it isn't all that strong. You did this for any standard cipher, it's complete noise, right? So next time you have an encryption function, just generate a picture and convince them to use AES instead. So I would imagine that this is not quite done yet, but let's. Okay, so this is still working, right? We'll come back to it later, though. So GA1 is a cryptographically weak function. Oops.
We're going to show this is the traffic of a normal operator, like cipher.
Do we want to see cipher traffic? I mean, so you can imagine that with the tools he just showed, we can feed this crypto cracking beast, right? I don't think we need to show that just now. What needs to be done around gprs to mitigate this, what I think, high risk, especially in the countries that don't encrypt at all, needs to be a combination of several things, and it can't be just calling gprs the outdated old protocol that will go away soon. So gprs is still the predominant mobile data protocol for rural areas. You may see UMTS more often not on your phone, but also you don't want to lose connectivity whenever you don't see it. So GPRS is the only wireless protocol that currently covers whole countries. Everything else, 3G, 4G, WiMAX, only covers hotspots. It may cover a large percentage of the actual data usage, but not of it. So there is nobody challenging GPRS as the predominant data for large countries. And the data traffic is only going to grow. Here's Cisco's predictions. And so will the usage of GPRS in all the areas where no alternative is available. So to make this standard that's here to stay secure, the users need to become more aware, as do the application authors, and at the same time the networks need to improve. Now, a year ago I probably would have focused on the first, but having done the whole GSM research and worked with a couple of operators, they have woken up. One of the German operators has implemented all of the measures we called for in December, and they're asking for more food in terms of kind of evolutionary steps in which they can progress. Around GPRS, no such progress is observed yet. However, of course, the problem wasn't quite as obvious until today. So there is hope there's hope in reminding people of this being an important network that's very much in need of fixing. But still, all of you as users and application authors, you can contribute to more security too. Of course, GPRS is, in many eyes, no other than any other internet connection, and as such, untrusted. Right? The network operators won't tell you that and won't advise you as such when you are buying the private APN and this package of GPRS security. But still, don't take their word and use this as you would use any other internet connection, meaning use SSL over it. We do find that websites like m.facebook.com, they don't even use SSL at all. I haven't even seen a button on it where you can switch on SSL. So the mobile site of Facebook, which on the internet is probably heavily attacked and secured through that website, is completely open when used from a mobile phone, at least through that URL. There's many other applications on iPhones and otherwise that just forget to turn on SSL encryption. That's different from those SSL bugs they found in the iPhone, where even when it's turned on, you can give it a wrong certificate chain and will still talk to you, which would be interested when combining it with the whole man-in-the-middle fake base station scenario, but not so much for passive intercept. So if you are an aware user, check your phone for usage of this, maybe through using his tools and then sucking the key out of your phone and comparing what it sends and what it should send. We haven't and won't yet release the encryption function, so this kind of self-pen test type activities a few months out, but it will come. The network operators, on the other hand, what do they need to do to make this an internet age communication network? Well, first of all, they should adapt all the lessons they have learned when building UMTS. It's ridiculous that the same companies run two completely different security levels and have the phones switch between them all the time. So either one is way too strong or one is way too weak, and the latter, of course, is the case. So backport two good ideas from UMTS into 3G. One, mutual authentication. Make the phone challenge the base station for whether it actually is your operator's base station before connecting to it or sending crucial data through it, right? This isn't in the standard, but given that SIM cards today are warehouses for Java updates, and the operators load and unload these Java updates all the time for ridiculous purposes like checking when you're roaming where and updating some local databases and all of this. Why not add a little Java to challenge some remote server? A little challenge response protocol, execute maybe DES. There's DES on every smart card, to make sure these phones are not anymore connecting to fake base stations. On top of that, of course, do use the UMTS encryption cipher, the Kasumi cipher, which is called different names in all of these standards. Here it's the GA3 algorithm. As a long-term measure then, of course, ensure that the generic attacks, brute force, for instance, won't be feasible against these networks anytime soon by switching over to a 128-bit key. The phone already has a 128-bit key inside, coming from the UMTS SIM card. So the same SIM card generates completely different keys in this phone for GSM, GPRS, and UMTS, and they're different size too. But why not just have them all the same size? So the SIM cards are up for it. No phone, however, is. Today, not even, this is, I think, a state-of-the-art phone, BlackBerry. Not even, this phone doesn't even support the GA3 function. It does support it, actually, and in some secret menu, you can switch it on. Right? So they ship it switched off. WTF. Lots going wrong in this industry. So, but you can see that a couple of steps needed until we're at the point where the networks can again claim they're providing a secure transport channel for whichever application. With that, let me check on our little terminal here again. Still working, so we'll keep checking on this. Of course, this is working on random state, so it takes different amounts of time. Quick announcement for all of these, all of you that actually want to try this capability, because they may come from a neighboring country, want to do that local customer information activity with us. So get an Osmocom phone. There should be plenty available here. Many of you already brought some. We may have a couple spare ones if you really want to do this, and don't find one. Then start playing with Luca's firmware when it's up tomorrow. We'll post the Git link on our website. Also, if you really mean it and want to do multi-channel capture and all of this, build a faster USB cable. Dexter will host a workshop. He brought pieces for, I think, 25 of these fast cables. So this should be a nice workshop where you solder your own fast cable for these phones. I'm not sure when, where, but there's a wiki apparently for these workshops. Yeah, and then we should create a mailing list. We totally forgot about that. So that too will be on the webpage. So start exchanging ideas and especially results on that mailing list. Encouraging people to call their local operator and pressure them into switching off Skype monitoring and switching on encryption. With that, thank you very much, and I hope you got some questions for us. Thanks. No. And just in time, before the first question, this is the super secret GA1 state that this encoded. So this probably is the first public announcement that the cipher has been found, but also that it has been broken through a Gaussian equation solver based on some set solver ideas that Mate Soos had. This isn't even using the set solver yet, so there's lots of improvements, especially in time. You saw how long this took now to be expected. So thank you, Mate.
Okay, now we have about 10 minutes left for questions. Preferably queue up at the microphone. I don't want to run to everyone.
Do you say GPRS all time, and in the first sheet there was GPRS and Edge? There are some different techniques or something, or can I put it on Edge too?
Everything we said today applies to Edge, security-wise, cryptography-wise. However, these phones, these particular phones we use as a sniffer, don't capture all of the Edge modes. So
not yet.
Not yet. So in your pen test, you may find that some data slips through this phone just because of the age of the phone. But of course, this being unencrypted in some countries, somebody will build an intercepting device for all the different modes.
Any more questions from the flow controller maybe? No? Okay, then please give a warm hand to our speakers and, okay. Just, yeah.
Oh, there's another question? Okay, go ahead.
Okay, it's Peter. In which countries have you tested this attack?
No comment.
All right.
Okay, then have a nice evening. This is was the last talk in this hall, I think. There's one in the other hall, but otherwise, sleep well in your Bettgestell.